Let's practice our properties of limits. Here we have a nice polynomial and we want the limit as x goes to 2. I would start by saying, well, the limit of a sum or difference is the sum or difference of the limits. So I could say this is the limit of 5x cubed minus the limit of 7x squared. Once you write limit as x goes to 2, you don't need to keep writing the x goes to 2 unless something changes about that, which is pretty rare in this chapter at least. So you can just abbreviate by writing limit. So that's because the limit of a limit of a difference is the difference of the limits. So we'll write that here, limit of a difference equals the difference of the limits. And then this 5x cubed is a product, right? So we can say the limit of the product is the product of the limits. So that's the limit of 5 times the limit of x cubed. Remember, I still mean the limit as x goes to 2. I'm just kind of shortcutting that part. And the same thing here. This is a product, so I can say the limit of 7 times the limit of x squared, again as x goes to 2. And this is the limit of a product equals the product of the limits. You don't have to do this justification for every homework problem or even for most homework problems. It's just demonstrating how we would do it if it was required. And then what can I say? Well, the limit of a constant is a constant, that same constant. The limit of a power as x goes to a constant is just that constant to the power. That's one of the properties we're given. You can do it by doing more limited products because x cubed is the product of 3 things, right? X and x and x. And then we can say this is 7 and the limit of x squared as x goes to 2 is 2 squared. And the exact arithmetic is not important there. We're basically done with all the calculus. So that's how we can apply the properties of limits step by step to get a final result. You wouldn't be surprised to find that the limit of a polynomial is just whatever you get when you plug in the c value to the polynomial, and that's another property listed in the textbook. Let's take a more interesting thing now. Let's say the limit as x goes to 0.9 of x cubed minus 0.9 cubed divided by x minus 0.9. Why is this interesting? That's basically a difference quotient for x cubed. Here's the difference of two x values, x and 0.9, so that's like delta x. This is like f of x minus f of 0.9. So this is basically asking what's the derivative of x cubed at 0.9. Well, let's use our properties of limits. So we'll say the limit of a quotient is the quotient of the limits. So this is the limit of x cubed minus 0.9 cubed over the limit of x minus 0.9. This is a polynomial. We can just plug in 0.9, so we get 0.9 cubed minus 0.9 cubed. And in the bottom, that's another polynomial. We get 0.9 minus 0.9. On the top, we get 0. On the bottom, we get 0, which is indeterminate. So we kind of hit a roadblock there, right? We got divide by 0, and it seems like we should just give up. Well, that's the big thing about limits. Plugging in directly can give you an indeterminate value, but doing algebra a different way can actually lead you to the right answer. So if you get 0 over 0, do not give up. So we'll say do not give up if you get an indeterminate form. Like 0 over 0. The whole reason limits were invented was to allow us to deal with things that would give 0 over 0 if you plug in directly, but if we use the properties of limits, then we get a better answer. So if we're not giving up, what else are we going to do? Well, graphing's not a bad idea. So if you graph it, you get something like this. And we know now that there's kind of a hole at 0.9. And that hole is around 2.4-ish. It's interesting, if you graph it on Desmos, it won't show you the whole because it can't get, it doesn't evaluate it exactly 0.9 necessarily, so it doesn't know that it's indeterminate there. Let's go see what Desmos does do for this. All right, here we have the function we're dealing with, and I said it's basically a difference quotient, so I'm calling it D rather than F. I'm trying to plug in 0.9 exactly, and we get undefined. That was that 0 over 0. What if I tried to plug in something near 0.9? I get 2.54 or 45-ish, but I want to sneak up on 2.9, so I'm going to put a 0 here. I get 0.901. I get 2.43. Put another 0, get even closer, even closer, even closer. Does it seem like there's a pattern here? Even closer, x is getting even closer. It seems like we're getting an answer, but as I keep putting in more zeros, wait, what's happening now? Did you see that I lost a 0 here in the y values? Here I had, what, 5 zeros, and you would think, it seemed like as I put in more zeros in the x value, getting close to 0.9, that I was just getting more y values here and the more zeros in the y values, and I was just going to get 2.43. So what if I put in more here? Now I start losing zeros, and I've lost all those zeros. It seems like 2.43 isn't maybe the right answer anymore. I'm going to put in another 0 and another 0. Now it's 2.55. Put another 0, now I get 3. This is crazy. Put another 0, now it's undefined. So apparently you can't trust computers to handle problems like this. It's not Desmos' problem. This is just the way basically all computer software is written, that it can't handle long strings of digits like that. So we really do need that algebraic way of seeing things. So let's go back to paper and pencil. So in our graph on Desmos, I guess I got this part wrong. It really looked more like that, but that's not the big deal. The limit still looked like it existed. There was no like shooting off to infinity or crazy oscillation or anything. So the limit can still exist. Even if plugging in gives 0 over 0. So there we're just eyeballing and saying the limit seems like it exists and seems like it's about 2.4-ish. So let's see if we can do some algebra to get a better answer. To simplify the algebra, I'm going to switch to squaring instead of cubing. You could really go play with the cubing if you want to. So we're going to switch to squaring instead of cubing. So we're going to say, what's the limit as x goes to 0.9 of x squared minus 0.9 squared over x minus 0.9? What algebra can we do on this? Well, you might remember there's a formula for factoring the difference of squares, and that is x minus that thing times x plus that thing divided by x minus that thing. And then what do we notice we can do, algebraically at least? We say, hey, we can cancel that stuff, right? So we cancel that part with that part and say that that seems to just give us the limit of what's left, x plus 0.9, and that's the limit of x as x goes to 0.9, so that's 0.9, and add that. So we get 1.8, and that's entirely appropriate, but it turns out, so this function is the same as this function before we cancel stuff, but this function before we cancel stuff is not the same as this function, because this function is defined everywhere. This function is undefined where we get that divided by 0. So these two aren't exactly the same function. Why is it we can say the limit of this function is the same as the limit of that function, even though they're different functions? Well, they're the same everywhere except that one point. So this equals right here has to be justified. So it's justified by what some books call the matching functions limit law. Which you could abbreviate MFLL. Our book calls it something different, which I'll show in just a sec. So here's our book's version of the matching functions limit law. It's the limits of functions equal at all but one point, which is what matching means, that the functions are equal at all but one point. So I guess you could abbreviate this as LOFEAABOP, or matching functions limit law, MFLL is maybe a little shorter. So when you're doing algebra like this and canceling things from the top and bottom to avoid the divide by zero, that's when you need to cite the matching functions limit law or the LOFEAABOP. You don't need to cite it going from here to here because those functions are exactly the same. They have the same domain, they have a divide by zero in the same place. It's going from the uncanceled version to the canceled version where you need to cite it. And our next thing will be about something called the squeeze theorem.